Hello, hello. I am coming. I'm here. Hello, hello. I'm saying hello into space. I actually don't know who I'm saying hello to. It's an experiment. Uh, saying hello. Now I'm saying hello to Katie, and I'm saying hello to Maria. That's awesome. And I'm saying hello to Paulina, and I'm in the back, and I'm saying hello to Claudia, and and I'm saying. Hang on. And I'm saying, what am I saying? I'm saying good afternoon to Katie. Oh, so that's a hello and a good afternoon. Okay. Good afternoon to Brandon. That's a good afternoon to Jenna. That is a good afternoon to Logan. That is a good afternoon to Alexis. That is a hello to Shy. Good afternoon to Shirley. Good afternoon to Maria. So that's a double. Good afternoon to Claudia. That's a double. That's a good. And there's Josephine. Good afternoon. And good afternoon, Victoria. Rock and roll. And Stephanie and Alexis and Jada. And okay. And Shawnee. And I feel like I forgot. And Brand. I said Brand. Logan. Okay. Well, anyway. Hello. Okay. And is the board boom? Okay. Ah, yes. And hello, direct person whom I see and whom I won't acknowledge by name. All right. Awesome. Let's get this party started. I want to have you quick question. Lab 5, have you done the slow down? The lab that's called slow down? Have you can I just get a quick electronic or any, that's a yes, Claudia. Okay, thank you. So you've done yes, you finished it on Friday. Awesome. Okay. Does that mean your report? Actually, that's perfect. Thank you, Paulina and Claudia and everybody. But does that mean when you say you finish it, does that mean the report is still due? Has there been have you turned in a report on it yet? No. Okay. Your report submissions. Okay, wait. I saw Claudia's face and I saw our report submissions are not opened. Wait, not opened. That means the portal's not like, wait.
Like there's no assignment on Google Classroom for them
Oh,
yet.
okay, perfect. Okay, thank you. And whose voice was it? Wait, that was like a voice. That was like, was that Pauline? That
That
was?
was Maria.
Oh, great, thank you. Because the chat was right in front of your face. I'm sorry. I mean, right in front of your, not in front of your. Great. Okay, thank you, and thank you, Paulina. Okay, and please submit for points, all you guys who are using voices and saying helpful things. No, that's actually really helpful to know because that's perfect. Okay, because I want to like help. That means there's still actually an opportunity for me to possibly be helpful before you turn that in, which would be my goal. It also means that we're like right in the right place as far as I'm concerned. You might recognize this diagram on the front. That has to do with that lab. So we're gonna. My goal is to get to that lab today. The one thing is, I want to just quickly finish the problem that I started yesterday from homework 8, and I have to apologize. I have to backtrack slightly. I don't want to spend like a huge amount of time on it, but I have to backtrack slightly because problem 8. Um, First, I'm going to backtrack slightly. Hold on, let me just bring up the thing. I'll explain. First, I didn't even realize that there was a hand in the problem, I think, when I was first explaining it. And then I said, oh, there's got to be a hand pulling, or, there's got to be a hand doing something. And I threw in a hand. Then I read the problem more carefully later, as we should always do. And the problem actually specifies that the hand is pushing from the right, which is not, I don't think, what I drew or what I said. So I'm going to just back up quickly on that and just do it cleanly right now. Pardon me. I don't want. It's like it's not the most interesting problem in the world, but it's okay. So, but it's worth getting correct. So here it is. So, okay. 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 Just so I'm like really, I'm not going to re-explain everything, but I'm just going to redo it cleanly now for the notes and for clarity. Like, here's a situation: we have M1 and M2 next to each other. We have on a table. The table has is a rough surface, right? And according to the problem, and this is what I just there's a hand pushing everything to the left. Okay, just according to the problem, and I missed that yesterday. And so the whole thing is accelerating to the left. So this so that's a system schema, right? Center of Earth is pulling on this a system schema of the M1, M2 system. And by the way, the purpose of this problem, if this problem is meant to practice anything or demonstrate anything, it's meant to show what can happen when we have a system of masses. And the bottom line strategy or a takeaway concept of a system of masses is that you first always zoom out as far as you can at first when analyzing the problem. You collect always as a strategy, maybe write this down, you collect as many masses with the same acceleration as you possibly can when you're first analyzing a problem. That to the same, which we've been doing all along, we just haven't called attention to it. Like even in the last problem with a duck, you notice, I mean, not to be dumb about it, but like when we analyze the duck, we don't analyze a molecule in the duck's pancreas. Like, right, we're physicists, not biologists or chemists. So even though the duck is made up lots and lots of particles, if we're willing to believe that those particles on the whole are sharing one acceleration in the reference frame of the lab or in the reference frame of the elevator, then we treat the whole duck as a particle. And so we're being explicit about this now that with M1 and M2 are like attached in some way, or if for whatever reason M1 and M2 are accelerating through the lab at the same rate, then we at first analyze them as macroscopically as we possibly can. Okay, that's the idea here. But by doing so, by getting the acceleration of the whole thing, it turns out that by the end of the problem, we can zoom in and learn something about internal forces, as long as we have first ignored them and treated the whole thing as one large system. Let me find a way. The law, Newton's second law, is F net equals ma. The sum of the external forces on a system accelerates that system. What accelerates the system is forces from the outside, right? So this is a problem that's sort of meant to be probing or pushing us to embrace the subtlety or the nuances of what we mean by external. And what we mean by external is as far out as we can possibly be given one constant acceleration. And once we've analyzed things externally, we have the ability to go in and be more internal. Okay, so that's the purpose of the problem. But anyway, I'm just redoing it now for anybody who's just joined, or just cleaning it up because I didn't realize that there was a hand pushing from the right. So there's my system schema. And you can stop me at any time if there's any lack of clarity, but that's the system schema for problem 4. Then the free body diagram for the 2 clock system. And then, right, okay, the normal force. Okay, so okay. Okay, again, what I'm writing right now is mostly a repeat of yesterday. It's just to get it one clean, no confusion issue. So that's the acceleration of it. Okay, that's the acceleration, the horizontal acceleration of the 2 block system. Oh yeah, and we already got right. We got sorry, and x. Okay, and now we're just okay. And this is the point now. Notice the pattern of the problem. First of all, one part of the pattern or of the solution, one part of the pattern is that we tend to analyze, we always analyze one axis at a time. That is key, that is key, that is key. We tend to make the x-axis the one along which acceleration is occurring. We always have to break up all forces to make sure all components are lying only along axes first, but that already was the case in this problem. And then we always analyze the axis with the normal force in it first. That's part of the strategy. Because generally speaking, we would need the normal force for the friction along the other axis. Although in this exercise, they just gave us the friction. So we're doing that pattern. But now notice the other part of the pattern. We get the acceleration of the whole system. We got the acceleration of the whole system. It was 0.75 meters per second squared. Like that's the acceleration of the M1, M2 unified entity. Again, and that's something that Claudia had asked about like 2 weeks ago. Like, can you treat them all as one? And yes, you can. But the reason that we zoomed out all the way first and got the acceleration of the whole system is now we're able to zoom in. So I'm on F now. In F, it says, and I think this is where like we left off yesterday, it says now treat M1 as its own system, zooming in, right? So if we draw the FBD for M1, notice now this is different from the other FBD. Like we've got the weight down, but it's just the weight of M1, right? We've got the normal force up from the table, presumably, okay, and specifically, this was Claudia's question, like, or the normal force is, this normal force is only supporting, this is only the normal force from the table supporting the weight of only M1. So, it's not as large as before. And we're only drawing things that are touching M1. Well, there is friction touching M1 from the surface of the table. There's no hand. The hand, okay, this is what there's no hand. If we were told in the problem that a hand exerts a purely horizontal leftward force onto M2, it means the hand is touching M2. So the hand is not touching M1. Like, that is important. That's one of those, it's so simple that it seems too simple almost, but this goes back to my original rule, like what forces are gravity and anything directly touching something, and only things that are directly in contact, other than the grand exception of gravity. So the hand is not touching M1. So the hand is not a force on M1. And furthermore, and that's just like with the sled problem, the child was not touching the sled. The string was touching the sled. And granted, a child was touching the string, right? But we don't put the child in the sled problem. We don't say that a child is responsible for the sled accelerating. What's responsible for the sled accelerating is the string. Similarly here, the hand is not responsible for M1 sliding to the left. What's responsible for M1 sliding to the left is the force from M2, which, by the way, strictly speaking, is a normal force. I mean, in fact, I'm going to call it that. I'm going to call it N2. It's a normal force. It's a surface pushing against M1. It, by the way, also means that if M1 and M2 are rough, then there could absolutely be friction between them. Only I don't care. First of all, because the problem doesn't get into that. It doesn't ask anything about that. But also, like, the friction between M1 and M2 would be sliding, rubbing would be along the y-axis. Excuse me. So it would only be relevant if anybody ever asks me anything about how M1 or M2 are sliding up or down relative to each other, right? But I'm saying that force that's on M1 now is N2, the normal force from mass 2. And then there is indeed friction on M1. So this is a different diagram from the other one. Please understand that, like, okay, I'll move on in a second, obviously, but not only is the hand not in this diagram now, because the hand, even if you think the hand is indirectly doing something, it may be, but it's not directly doing anything. And number two, there suddenly now we're acknowledging, we are now for the first time in the problem acknowledging an internal interaction between the two objects. And we're acknowledging it because we're now treating one of those objects as its own thing. So this new force that's coming into play, the N2, that's now it's a external force from the outside of the world acting on M1, just to say that. Okay. Okay. So this is our free body diagram. Sorry. So now compute the magnitude of the force exerted by M2 on M1, which I'm calling N2. So the question, what is this, is what it wants to know. Okay. Now, again, that's a normal force. How do we know normal force? There's no formula. I'm just looking in the chat. Sorry. Okay. There's no formula for it or anything like that. We do F net equals MA always. And and it's a vector equation. We're doing it in the X axis. So the force is on this. So we have now we're solving for the normal force. All right, so it's this. Oh, sorry. Okay, so we're talking about on M1. I'm just changing the view on the screen here. Do we say hello to Josephine? I think we did. Sorry, I'm going back and forth between the sheets. Yeah, okay. M1 is 3. So M1 is 3. We know that. The friction on M1, we're just told, is 1.5. Do we know the acceleration of M1? Yes, we do, because it has to be the same as the acceleration of M1 and M2. They're all accelerating the same. So that's why we got that first. That's why we zoomed out first and got that number 0.75, right? So we get 2.25 plus 1.5. I think these numbers are right. And we get 3.75. And that's the answer. That's the answer of the force exerted. And wait, that's all. Sorry. Oh, yes. Okay. So that is F. That's F sub 2. That's the magnitude of the force exerted by M2 onto M1. Right now, it asks us to go over and get the magnitude of the force exerted by M1 on M2. Now, let me pretend this was an exam or something for a minute. Like, it's now asking for the opposite, for the force of M1 on M2. This is a good, like, if I were in an exam right now, what I would think to myself is, okay, this is an opportunity for check. Like, I see what's going on in the reasoning of this question. I would say to myself, I had better get the same answer. Right? The force from M1 onto M2 by Newton's third law had better be the same answer as the force from M2 to M1. Maybe if this were an exam, I might even write that down. Oh, well, first it's asking for a free body diagram. So I'm going to draw the diagram. But just to see where it's going, I better get the same answer here. But there's a method that's being implied. I mean, I just figured out a method for solving the problem. So, I mean, if this were an exam and I just wrote down it had better be the same Newton's third law, like, honestly, if I wrote that and I'm right, like, I should get full credit for that. That shows I know what's going on, and that's smart. I mean, after I draw the diagram, which I have to do. But what's even better is if you see what's going on, like, why not actually do it out and then get the same answer, and then you'll really know you're doing things. Like, it's a check on your first procedure if you do it out and then say and add, or you could even predict, like, prediction, this should be the same by Newton's third law, then do it out and say confirmed, this shows that everything's working. Because then if you get that it's not the same, something, you probably have to go back and fix something. So it's a good, you see what I'm saying? So that's why we're doing this. So G. Okay, so G is drawn FBD for M2. So M2, well, M2 is more complicated. This is probably why I was asked to do M1 first, because M2, there is the hand, like, the hand is touching M2, right? M2 also has the friction, and M2 also has the force on it from M1, right? Like, going in the other direction. All of those are acting on M2. It's the more complicated object. No wonder I'm looking at it second. And it has its own weight down, and it has the normal force on it up. So now compute the magnitude. But there are a lot of forces on M2. And stop me if you don't understand that. Wait, I'm just looking at the chat. No, we're good? Okay. All right, so hand minus friction minus N1 all has to equal M2 times A, right? And how did I know how to do the pluses and minuses? Because I'm just looking at my arrows. One arrow is going to the left. Left has been positive the whole time because that's the direction of acceleration. And the other two are negative. So Right, okay. So this is the friction on this guy, so that's 2.5. And the N1 is what we're solving for in this case, even though we hope it's going to be the same thing as before. M2 is 5, and the A is the same A as always, 0.75, right? So now this would be 7.5 minus N1 equals 5.75, which is 375, right? Should be. Yep. Okay. And so then N1 had better equal same thing, right? Yes, and thank goodness. Okay. And so, right, if we do it all out, we get the same magnitude as before. Right. Okay. So, and right, so it worked. Like check. I mean, right, because we got 375 on the page before, so that's great. And by the way, some of you who are really paying attention might even be thinking, oh wait, there's something in the chat. I wonder if that's exactly. Wait, there's something in the chat. I wonder if it's exactly what I was about to just bring up. Let's see. Okay. No, it's not, but that's fine. Okay. Fair question in the chat. In the direct chat, someone says, still confused about where the N1 came from. Well, part of me what might be confusing is the name, is the fact that I'm calling it N1. Forget what I'm calling it for a second. What we're talking about in that, but great question. I'm glad someone has the guts to ask. What I'm talking, and I'm really going to want you to tell me whether I've answered it or not. Like, tell me honestly. What I'm calling N1 in the diagram is the push against, let me see if I can I'll screen share the picture in a second. It's the push onto block M2 from block M1. Like we're now zooming in and looking at each block individually. In this case, we're looking individually at block M2. We're defining it as the system. So it's being touched on its left side. It's being touched by block 1. And specifically, if M2 is sliding to the left because of the hand, it's like jamming into M1. So M1 is jamming into it. M1 is like slowing it down. If M1 weren't there, M2 would be going a lot faster, would be accelerating a lot faster. So in summary, what I'm saying is that where I wrote N1 up there, what I mean is the right word contact push from mass 1. And I'm definitely going to wait until I'm sure that you're sure that you know what I'm saying, because this is a great question. To everybody, the N1 that's in the diagram there, you can call it push from M1 or something if you like. What I'm saying is it's there in this diagram for the same reason that N2 is in this diagram. In this diagram, we're zooming in on M1. When we zoom in on M1, we're saying something's touching M1 in addition to the table. What's touching M1 is M2. So M2 is, and M2 is on the right of it. Not only is it touching it, it's like the whole only reason that M1 is going to the left at all is because there's a block behind it, shoving it along. But similarly, M2, if we're focusing on it, it's being shoved along by a hand, but it's got this big M1 thing in front of it, shoving against it. This is very important. It's a very good question. I would like to know, I want to make sure that the person who's asking me that is like okay with what I just answered. Like I am very, oh, okay, cool. Okay, thank you, awesome. And to everybody, like, and I'm glad, this is like why the problem is worth it. The problem is like sort of a slog until this point, and whatever, and we'll move on in a second. But really what this problem's trying to show is like the force that direct chat person is asking about, what I'm calling N1 and N2, they were not in the diagram. They were not in our analysis at all when we were zooming out and looking at the whole thing as one collective mass. They only became relevant once we zoomed in and we're looking at individual masses. Again, F net external equals MA is what we're really saying here. And then the last thing I'm saying about it to anybody else who, I mean, I totally appreciate that person closed the loop. I'm calling it N1 or N2, whatever, because I'm also trying to reinforce that those pushes to the side on these blocks from the other block, they're normal forces. They are normal forces, just from not the same one from the table. Okay, but if there are any other questions, that's good because I want to move up. But sorry. Okay, cool. I'm glad there's follow up of this. So the hand is pushing one. Yeah, totally. So what Maria is saying in the public chat is 100% yes, like is what I'm saying. Like the hand is pushing M2 one way, but the M1 in front of it is pushing the other way. Like, yes, M2 is being sandwiched. And in fact, yes, I'm glad you guys are like pushing me on this. Okay, cool. Okay, sorry, there's a slight interruption here. There's going to be a slight. I just do something in a second for someone else. But yes, these are good follow-up questions. And look again, like notice, it is kind of part of what we're trying to show in this last bit of the problem is that M2 has a lot going on. It has more things affecting it directly than M1 does. Bottom line, because M2 is being touched by the hand, M1 is not being touched by the hand. Yet everything works out. Like everything like, I don't know how to say this any further, but M1 accelerates at the rate that it's supposed to, not because of the hand, but because of M2. And M2 is what's shoving M1 along, causing it to accelerate that rate. But that means by Newton's third law that, wait, I'm looking at, that's cool. Wait, sorry, I just got, okay, I'm getting, yeah, all right, I'll finish the sentence. And I like what Katie's putting in the chat. I'm thinking about that. That's cool. Okay, like lots of things are happening. So something about this problem, I'm glad we cleaned this up. Someone's asking to go back to that. Okay. The reason that M2 is going forward is the hand. In fact, it's really the net effect, the difference between the hand and M1. The reason that M1 is going forward is M2. What's making M1 go forward, M2, is, am I saying this correctly? Yeah, is actually resistance to M2 from M1. Like everything is doing a different job on a different, but all the numbers work out. And M1 and M2 are obeying Newton's third law and everything's going forward together. Like, yeah, I mean, these are good questions. I'm going to pause. Sorry. And then Katie's thing is cool. Is it like, it's similar to the ground pushed against the sled, excluding the tension of the thread. Yes, I think I agree with that. Oh, got it. Thank you. Okay. I think I agree with that. Yeah, I do. I mean, the ground pushed against the sled, I think, in a frictional way. That was the friction from the ground. But yes, right. It's resistance, as in it's a force going in the opposite direction. But as long as it's smaller than the other force, then the net force gets us going forward. Yes, like I like Katie's contribution. Yes. Now pause for a second. Pardon me. There's something else is going on totally unrelated. We'll go back. Oh. Just bear with me for 1 second. But we're going to move. Oh, we're going to do the angle now, which is the other reason I wanted to do this, is to do the angle. Just bear with me for a second. Okay. So now we're gonna do the bonus part here. Whether you did it for homework or not, we're gonna do it here because we now have to like worry about angles as per your lab. Okay, so let me go back. I'm all over the place here. The bonus. But these are great questions, and keep them coming if there's wait, Art, you got it. Okay, you got it. No, the more questions the better. For reals is okay. Okay. Now it says extra credit. Assume that the hand exerts a force of 10 newtons, but at an angle 60 degrees below the horizontal. Oh, and so this is really like what Katie's saying. Now, this brings us back kind of like to the sled situation. 60 degrees below the hand is but from above, pushing downwards. Oh, yeah. Oh, yeah. Okay. Wait, let me think about this for a second. I mean, yes, this is just like the sled now. I'm looking at the time, like, is this worth? Do I want to answer all of these questions? I'm not sure I want to re-answer all of these right now. I want to get to the lab, but well, let's see. Okay. But yeah, I'll do. But everything else is the same. But now the hand. And then the hand is like that. And yet remember, angles are we always try to measure our angles with relative to horizontals, right? So that's 60 degrees below the horizontal, but it's still the same magnitude. It said and everything else is the same. Okay, all also the same. Okay, okay, so I'm going to try to do somewhat quickly. The system ski. So I'm just redoing the problem now, but with the hand at an angle. The important thing is to now practice how to deal with angles, because again, where this is all heading towards is the lab, right? The lab combines these factors: friction, angle, gravity. It puts them all together. The one thing with the lab is that the whole thing in the lab is on a tilt. Right. But if we can do all of these elements here, having practiced twice with these two different problems, we should be able to do apply it to the lab. So I'm just redoing this as it's asking. It's asking for a system schema. The system schema is exactly the same because all we've changed is the direction of one of the forces, and system schema doesn't care about direction. It's just there to identify the forces. So the system schema is the same, 4 forces. Then what's the FBD of the whole system? Here's the FBD of the whole system. It's almost the same. But the hand is now at a tilt, right? That's the FBD. Oh, that's the new FBD. And I think the normal force is bigger now, if you think about it, because the hand is, and this is Katie's point, or like this is related to Katie's point. Like now that the hand is not just going to the left, but going left and down, that means the hand is like pushing somewhat down on the blocks. So the normal force has to do more now than it did before, because it not right, it's not just supporting the weight of the blocks, it's supporting some of the downward push of the hand. So that normal arrow has to be, I think, bigger than it was before. I'm just predicting, we'll see. Right? It's definitely going to be bigger than the arrow that signifies the weight. Right? And the hand arrow is I think still longer than the friction arrow. This is just a sketch of, I mean, this is just approximate magnitudes, but that's our free body diagram now, right? But now it's asking me to redo all the questions. It's asking me to get the acceleration. Well, it's asking me now to get the upward normal force of the table and the acceleration of the two block system. This now, okay, I have to pause here. Like, I'm just redoing the questions, right? But now I have to stick in a new step on my own. Like, now that my free body diagram has at least one force that is not parallel or perpendicular to all the others, now I have to pause, explicitly choose my X and Y axes, and break up any and all forces that don't lie along the X and Y axes. I mean, in this case, that's one, the hand force, right? So I've got to, so in other words, now in order to solve C and D, etc., I now need to choose axes and resolve all force vectors into components which lie along axes, right? So I'm going to say, since the blocks are expected to accelerate horizontally to the left, I'm going to say that the left is the positive x-axis. And up is the positive y-axis, right? Those are my axes. Because the blocks will accelerate to the left, right? Okay, so that's my axes. So now I'm going to break up all forces into right, here's the hand. I'm zooming in on the hand. It's 60 degrees from the horizontal. So I always, now remember, there's a number of ways I could draw that. Like, there's a number of ways I could break this up, but it's not geometry, it's physics. The hand is an arrow. It's pointing down and to the left. So I break that up into some amount down and some amount left. But I always draw the horizontal first, and I make the two legs of this triangle tip to tail. Like this leg, I'm just moving this over. I'm not changing, I'm just moving it over. But like the whole idea is that that hand force, which was measured as being 60 degrees from a horizontal, I break it up into some amount left plus some amount down, right? And I always draw the horizontal first, and from the tip of the horizontal, I draw the tail of the vertical, right? And the hand was given, the magnitude of the hand was given, I believe, as 10 newtons, right? So this component, the adjacent component, is hand cos theta, i.e. 10 cos 60, yes. And this component, which I should have given myself more room, this component is hand sine theta, which equals 10 sine 60. Yes. In other words, 5 newtons, and this is 8.66 newtons. Yes. So now that I've zoomed in and broken up the hand which was the one issue, now I take those components and I substitute them in for the hand in the free body diagram. So in other words, so the component FBD free body diagram becomes sorry, and I can go back to that. Wait, I'll go back to the I'm back and forth between screens here. If you need me to go back. Oh, sorry. Wait. I don't know what normal resistance is. Did a little differently with the thing. Well, as long as you got the same answer. Wait. Okay, I'm looking at Shawnee's. That's cool. But I don't know what normal. Normal force. Okay, grab it. Okay, as long as you did it. Yeah, as long as you got the same answer, that's cool. I mean, as long as you got the same answer and it wasn't a coincidence, I suppose. But here's the component free body diagram. It looks like this. We've got M1, M2G down. And this is of the whole thing still. This is back to the Claudia thing from like 2 weeks, right? I'm zooming out. So then we have and we've got right. And you notice, I mean, first of all, even though I already just solved for the numbers for those, I don't tend to put numbers in my free body diagrams. Like my free body diagrams are just trying to tell me what's going on. So I don't tend to put numbers in them. That's number one. But number two, and you can, so there's two, the point is now there's two vertical, there's a total of 3 vertical forces, right? There's the weight of the whole thing pulling down, but there's also the hand is pushing down somewhat. The normal force from the table is pushing up, and some component of the hand is pushing to the left while friction pushes to the right. So now if we want, so this is our diagram. Now we can do F net equals MA in order to answer the questions. Like C, the question is, what's the normal force exerted by the table? It's not the same as before, right? I mean, again, by the way, this is like the duck in the elevator. Like things are happening in the y-axis. And if things are happening on the y-axis, they affect the normal force. The bottom line, another way to think about the normal force is, what is it? It's 2 surfaces pushing against each other. What is that really all about? Like, how does one surface push against another surface? Well, if you really think about it, if you zoom in very far microscopically in your mind, you think about chemistry or something like that, and you realize what's on the outside of all surfaces, a bunch of electrons. What's on the outside of the other surface, a bunch of electrons. So it's electrons repelling one another that is really creating the normal force. And we'll talk way more about that in physics 204, but it's the electrons pushing one another, and they push each other in a manner that's sort of like springs. I'm not trying to get myself on a thing here, but I'm saying that, like, when you put something down on the table, it finds an equilibrium as though you were pushing down on springs. So when you start pushing harder, when this hand is pushing harder on the top of M2, the table like readjusts itself and pushes up more, as would happen if the table were a spring scale and you push down harder on the head of the duck. I don't know. I'm saying you've got to redo these problems now that the hand is on an angle, because the normal force is going to change. We're going to do So we're solving for the normal force in part C. Part C, the question is, what is the normal force? We're solving for the normal force, so we look at the axis in which the normal force is acting, which is the y-axis. And so we say N up minus hand sine theta minus M1, M2G down, all equals M-A-Y, and M-A-Y is 0. Okay, so I'm going to go to the other page now, right? So in other words, and I can go back in a second if you want me to. So the normal force has to be supporting not only M1 plus M2G, but also the vertical component of the hand. So we've got 80 newtons from the weight of the whole thing, plus we said 5 newtons, which is the vertical, in other words, 10 times, oh no, sorry, it's not 5, it's 8.66. 10 sine of 60, right? So the normal force is bigger now. It's 88.7 if I'm staying with 3 significant digits, right? That's the new normal force now that the hand is at an angle. That's the answer to part C. The answer to part D, compute the acceleration of the two-block system. It's going to be different now. Now we go to the... Now this part is a little unrealistic. Honestly, this is where I want to get to the lab. This is a little unreal. Honestly now, and again, I guess this was sort of the Katie point from before, or certainly related to the Katie point, is that, you know, the truth is that if you're pushing, if your hand is now pushing on an angle and it's affecting the normal force, in reality, that would affect the friction of this. It would actually slow down the whole thing even more substantially because of the friction. But this problem is not taking that into account. They're just giving you friction forces that, which it says in the paragraph, it's not really realistic, but because we're like warming up to the lab where you do care about that. But anyway, so D, the acceleration. Now we go to the x-axis. So we say hand cosine theta minus friction. Is that it? Yeah, that's it. Equals MAX. Right. And so that's 10 cosine 60 minus the total friction here, which is 4, equals 8A. So that's 5 minus 4 equals 8A. So 1 equals 8A. So A equals 0.125 meters per second squared, which certainly is lower than before. Right before it was like 0.375. And that makes sense because, I mean, even without an increase in friction, the fact is the hand, it's pulling just as hard as it was before, but it's not devoting all of its pull into horizontal acceleration. Like some of it's being wasted, just shoving down. Like some of it's being wasted on leverage, basically. So that's lower. Okay, I think. Well, okay, we can finish. All right. I think I'm going to leave that. Actually, I'm going to leave that at that. You could then plug in and do the rest of the problem if you like. I think that's enough of an illustration of how the situation is different due to the angle. I want to now move. I want to analyze the lab problem now. Or in other words, inclined planes with friction. We have 19 minutes left. Let me just look at the. Oh, can I go back a page? Yes, I may have. Was that a long time ago? Sorry. To this page. Yeah, okay, great. Okay. Let me know when. Okay, cool. All right. Okay. Okay. So now, well, okay. We have 17 minutes. What I'm going to try to do, I'm going to try to get to what I think is the heart of the matter with lab 5. But here, wait. Wait, great question. Wait, in lab 5, okay. Well, yes. Okay, sorry. Well, okay, hold on one second. So lab 5, yes. I was here. Here's, as far as I know, here's lab 5. Well, I guess it was probably a marble, not a block, but that's okay. No, wait, was it? You might want to tell me what in lab 5 did you do? Was it it was a marble roll? Yeah, okay, great. Thank you. Okay. Okay. I was just going to say I'd like to get to the what I think the heart of the matter is here, because I know you've already done it and you've thought about it a lot. So now my ideal is to refine any issues you have before you turn in your report. So yes, so there's already a question in the chat. I'd love to. Yeah, my ideal is with 16 minutes. If more of it is just me answering any confusions or questions you have, that's great. I will certainly prioritize those. So one question that's already in the chat is, you were told that friction plays a role, even though there technically was no rough surface. You were told that friction plays a role, even though there technically was no rough surface. Would I be able to explain this concept a bit more? Well, friction definitely plays a role. Yes, there is a rough surface. I mean, the plane is definitely rough. Like almost anything in reality is somewhat rough. Some things are rougher than others. But that slide that you put the marble on is rough. The only things that I know that are like essentially not rough would be like an air cushion on an air hockey table or on an air track, as I guess you use in Lab 1. Or something like that. I mean, the surface definitely is rough. What you might be, and you could tell me more if I'm not really addressing the question. Definitely, this lab is about friction. Yes. Now I'll say this: this might be what you're asking, or this might be the technicality that the lab is getting at. What is also true is that rolling, you are rolling in this lab. You're rolling a marble because it's like a lot easier to work with. It's a lot easier to reproduce. It's a lot easier to get, easier than like sliding something. It's easier to play with rolling objects than sliding objects. So you're playing with a rolling object. It is true. Sorry, someone's here. It is true that rolling severely cuts down on friction. And yes, the amount of friction that you're getting on like the whole purpose of rolling things is to severely cut down on friction. That is true. And in fact, if it were a perfect roll, like in fact, no matter how rough your surface is, if the marble were perfectly round, like impossibly round, so that at any given moment, literally only one point of the marble were in contact with the rough surface, then okay. Wait, I'm looking in the chat. I'm still in. Good. Yes. So it is true. So the person in the chat is saying, like, yes, they were thinking about the rolling issue. What is true is that rolling is meant to severely cut down on friction. And yes, it is true. And it does severely cut down on friction. And the way it does that is that, so this is a great physics question. The way it does that is that if you put something round on a table, like just as the bottom point is about to slide across or along the table, then that bottom point like sweeps up and a new bottom point comes down and comes into contact with the table. So if you're rolling perfectly, what you're really doing is pivoting, right? It's like it's like walking. I'm about to demonstrate, but I'm not in a physical. Like when you walk, if you walk or perfectly, like if you put down your foot, then you pivot off your foot, and just when your foot is about to slide back, you lift your foot and you put your other foot down, right? And you don't really slide, especially if you're wearing boots or something like that. If you're walking perfectly, in other words, you don't really experience kinetic friction if you walk sort of perfectly. And when something rolls perfectly, it's like a walk in that sense. The bottom point of the sphere is in contact with the table, and then just as it's about to slide or graze along it, it sweeps up and a new point comes down. So that's in a perfect roll. However, just like there's no perfectly smooth surfaces in the regular world or in your lab or anything like that, also, there's no perfectly spherical marbles. Gravity pulls, like the marble squishes a little bit, like a little bit, but it does squish a little bit on the table. So because of its own weight, it flattens a little bit. So even while it's rolling, it's actually acting a little bit like a steamroller, like treads on on one of those kind of trucks that go around. So there's a little bit of squishing, but enough to matter, and a little bit of flattening of the round surface that's in contact with the table, and that slides along the table, and you do get some friction, and it's enough to make this experiment work and to be measurable and all that. So I don't know if that. So there is. Oh, cool, great, and thank you for responding, for closing. Okay, so okay, great. So then that friction that happens, we treat like normal sliding friction, like it obeys all the normal rules. It happens to be a very low mu, which you find. Oh, sorry, didn't mean to do that. Which you find out, I think, by the end of the lab. So that's a great question. So here we have our inclined plane, and it's rough. Like I'm making it rough, right? So it has a given mu that we're calling mu sub k that happens to be low, but it's big enough to matter. So these are and then the other given in the problem is that there's some acceleration down due to gravity. Now, in your lab, of course, the thing goes up and then it goes down. The two trips have two different FBDs. That's crucial to the whole lab. I'm sure many of you have realized that already. The FBD for the up trip is different from the FBD for the down trip, and that's what makes all the difference in the lab. I don't a 10 minutes. So I'm going to do the FBD for the up trip first. Now, by the way, right here on this page, this is my picture. This is my step one. This is like I think it was Paulina or Maria. Someone was asking me yesterday, or maybe it's the other, like, do you have to, do the step method and everything for these? And the answer is yes. And like, here's a perfect example. Like, here's my step one DFP and my picture of the situation. It's not a free body diagram or component or system scheme or anything. It's just my picture, but it's crucial because it shows you all, like in the 9 minutes we have left, that picture shows you which way I'm thinking the plane is oriented. So all my diagrams that I'm going to draw now, or any of my diagrams, are going to be totally based on that orientation, and they have to be consistent with that orientation. So in my mind, the slide is going like that way. Yours might have been going the other way, but mine is going that way. So my pure free body, I'm going to skip the system schema for now. The FBD, the pure, for when the thing is going up, the FBD is, well, we got gravity pulling down. Gravity always pulls down. We've got the normal force perpendicular to the plane of contact between the surface and the object. So if the plane is going like in the way that it is, then the normal force is going like that, right? This is a pure free body diagram I'm drawing. Now, the object is on its way up. It's on its way up for this trip. Why? Because someone flicked it at the bottom it flicked it to get it going. but they just flicked it and then they walked away. So it's going up because it was given an initial velocity, but that was an initial velocity. Velocities are not accelerations, and accelerations are not forces. That V naught, as I'm sure many of you know at this point, but might have been confused about it first, the V naught does not go in this diagram. There's nothing shoving this thing up, right? It just was sent up. So now at any given moment, it happens to be going up. Gravity's pulling down. The normal force is shoving perpendicular to the plane. And since the object is going up, then friction is pointing down, right? That is the pure free body diagram for the up trip. That's it. Those are the only forces. That's the pure. And notice friction and normal are perpendicular to each other as they always must be. Now I'm looking at the time. We've got 8 minutes. That's the up trip. Now I can't do anything with that really until I get some components. I mean, I totally can't do anything because some of the forces are not parallel or perpendicular with each other. So something's going to have to be broken up into components. I'll do that in a minute, but just to be clear, the pure FBD for the down trip is similar in that gravity's still pulling down and the normal force is still perpendicular track. But now on the way down, the object's going down, so friction's opposing it. So friction is up now, right? These are the two different. This makes all the difference in the world. Is like all the magnitudes of all these forces is going to be the same in both situations. But in one situation, friction's pointing down, and in the other, it's pointing up. That's what's going to make all the difference in the ultimate fact that, as I'm sure you know, the times for these two troops are not going to be the same. It feels like they should have been. They would have been if there was no friction. But because friction, even though nothing changes its magnitude, friction flips its direction. So thank you. So that makes all the difference in the times. But now how can we actually calculate the times? How can we do anything? We need to break forces up into components. Now here is the big catch, the big puzzling or hard idea in all of this with 6 minutes left. We have to break something up into components. We have a choice. I mean, we could break up friction, but then if we broke up friction, and you might think that we should break up friction because it's like on a diagonal line or something, but if we break up friction, we also have to break up the normal. We could do that, but right, in other words, if we choose that our axes are like this, well, okay, so here's what I'm saying. We must create a component diagram. This is our goal now. And the key point is to create a component FBD, we must choose axes. Every time I've said that prior to this, it's probably seemed unnecessary because it already, like, what do you mean choose axes? Like X and Y, like duh, Yaverbaum. But remember I've said every time, we have to choose our axes explicitly, and then we're going to arrange all the components into those axes. Now we could stick with X and Y if we want here. And then gravity's fine, and we'd have to break up two forces, the normal and friction. But first of all, we'd have to break up two forces instead of one. But second of all, and here's the key point, what I've been saying every time is when you choose your axes, we should choose strategically. And we could do that, and we'll get the right answer, but it's going to be a lot of work. If we want to be strategic, we want to choose, as always, choose positive X to lie along positive A. That's what we've been saying every time, and this is why. This object is going to accelerate along the slide, like on the diagonal, right? If we're going up, it's going to, and if it's going to, it's on a diagonal. So let's make that our x-axis. Why? Well, because I've been saying it every time. But why have I been saying it every time? Because F net equals ma. And if the A is not lying along an axis, then A is going to have to be broken up also into sine and cosine. In other words, the reason it might have thrown a lot of people at first, it generally, or now you might have just like accepted it on blind faith. But the reason I'm going to break up gravity is because I'm choosing this as my x-axis and this as my y-axis, because that's the way the thing is accelerating. And I don't want to break up three things. I don't want to break up normal, friction, and acceleration. I mean, I could, but that's a lot of sines and cosines. So instead, I'm going to say gravity is the problem. Gravity has to be broken up. Here's gravity. Gravity is doing two jobs. It is pushing to some extent down the plane and to some extent into or against the plane. See what I just did? Now yeah, I'll leave it at that because we have 3 minutes. See what I just did? Like I'm treating a vertical line as the hypotenuse of a right triangle. No one ever said I couldn't do that. And I'm saying we should do that. Gravity, by pulling down, is actually doing two jobs. It's to some extent pulling along the plane, and it's causing the object to accelerate down. And to some extent, it's holding the object on the plane. It's right. Those are the two jobs. This is one of these is, so to speak, mgx. And the other is mgy. One of these is sine and one of these is cosine. Which one? Well, the theta that's given in the problem is right here. This is theta. That's what we know. The angle from the plane measured from the angle of the plane measured from the horizontal. The question is, where is that in this triangle? And I would claim to you, we only have 2 minutes left. I claim to you that if you think through the geometry, you'll realize that that angle that we know is this angle right here in this triangle. I can explain that more extensively next week. But if you think through the geometry, you'll realize it's right. I mean, one quick way of seeing it, is there a quick way? Well, hold on. We were running out of time, so I'll show you that next week. But so that's the angle there. Therefore, mgx is opposite it. So this must be mg sine theta, and mgy is adjacent to it. So this must be mg cosine theta. So that's where we get, and I know we have 1 minute left. That's where we get the component on the way up to be like this. And the component on the way down. Oh, sorry, this is the component down. So the bottom line, I know it's 130. Those two diagrams are the key to the whole thing. The whole ultimate thing is that when you are going up, and I know it's 130, I'm putting down my pen. When you're on your way up, friction and gravity are in conflict. So the net force is small. So the acceleration is small. Sorry, I just said that backwards. When you're on your way up, friction and gravity are working together. So the net force is huge. So the acceleration is huge while you're on your way up. That means the rate at which you're losing speed on the way up is huge. You lose speed really rapidly. You get to speed 0 really rapidly. You're done with going up really rapidly. On the way down, gravity and friction are working against each other. So it's a subtraction, not an addition. So the net force on the way down is really small. So the acceleration is really small. So you gain speed on the way down at a much lower rate than you lose speed on the way up. On the way up, your job is to run out of speed. You'll get to the top when you have no speed. So on the way up, you lose speed really rapidly. You get to 0 speed rapidly. You're done really rapidly on the way. Then you come back down and you gain back the speed really slowly. You never gain back all the speed that you lost on the way up, because your net force on the way down is smaller than your net force on the way up. That's the point of the lab. Oh, cool. Okay. Oh, cool. I see what's in, but sorry, I kept you over. And if anybody wants to ask any more questions about it, I'm here. I'm not going anywhere, but you got to go. I helped a little bit. Yes. Have a nice, oh, great. Yes. Have a great day. Thank you. Yes. Awesome. Thank you. Okay. Also, recording. If there's any questions or.